we still have 5 minutes. Probably you want to tell the experiment, your experiment in Indonesia.
Okay, so
because we have a experiment with full scale in Bandung.
Yeah. So basically, this project is a collaborative program between the UK and Indonesia. In UK side, they did the experiments on their behalf. In our side, we also do the experiment, but because the facility that we have here is more established, then we can undertake the full-scale testing, and we did that at Puskim. So we haven't shared the results yet because it is under the analysis. So hopefully within like several months we can publish and let you know if we do.
Thank you very much, Dr. Asdam, and again, give an applause to Dr. Asdam. Thank you very much. You may stay beside me or you can stay over there.
I think it's better for me to stay up there.
Okay. Now we have a second speaker with the title Performance Evaluation of Structures with Buckling Restrained Brace Frame Under Earthquake Loads, which is written by Dea Yunitasari and Dia Kusumastuti. And this paper will be presented by Dea Yunitasari from online. Is it right?
Yes.
Dea Yunita, Dea, are you with me?
Yes.
Okay. Please, time is yours. You have 20 minutes for present your papers.
Okay,
Please.
Thank you, Professor Suprabo. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, all participants. Good afternoon, all participants of the 5th International Conference on the Earthquake Engineering and Disaster Mitigation. First, allow me to thank you for the opportunity to present our research paper. My name is Dea Yunitasari, and the author team, Dia Kusumastuti. We are from Faculty of Civil and Environmental Engineering, Institut Teknologi Bandung. And the title of this paper is Performance Evaluation of Structure with Buckling Restrained Brace Frame Under Earthquake Load. Introduction. Under cyclic axial loading, conventional brace yields in tension and buckles in compression. The buckling restraint brace frame system, or BRBF, improve the concentrically braced frame system, or CBF, to solve the buckling problem. The buckling restraint braces have typical tension and compression forces based on yielding. So the buckling restraint braces have a symmetrical hysteretic character. A typical BRB element consists of a steel core plate that has ductile properties and a steel tube casing filled with grout or concrete to resist the buckling of the steel core, with a special connection at both ends. The entire effective length of the steel core that receives the axial force will be restrained by the casing so that there is no slenderness in the steel core and eliminate the buckling failure mode of the core. From all components of the BRB, the steel core is the main component to define the member capacity, and it will be designed in this research. To design an earthquake resistant structure with BRBF as the single lateral load resisting system in Indonesia, it must meet the requirement of SNE 1726-2019. Based on this code, The design of BRBF structure as a seismic fault resisting system is to be conducted with a seismic parameters of R equal 8, CD equal 5, and omega 0 equal 2.5. Moreover, the seismic design categories D, E, and F on BRBF have structural height limitation. In this study, we use the seismic design category D, and the height limitation is 48 meters. Therefore, the purpose of this research is to design a buckling resistant brace frame system using a procedure suggested by code, that is modal response spectrum analysis. Then we check the result using the another design procedure, that is linear response history analysis. Next, to conduct pushover analysis to find out the failure mechanism E 1726-2019. This is the structural models. The structural design is an office buildings with a symmetrical floor plan measuring 30 by 30 meters with an interspan length of 6 meters and a height between floor of 3.5 meters. The building is assumed located in the city of Bandung, and the structural model is 3D, and you can see that in this marked area is the brace location, and the bracing configuration is diagonal braces. In this study, the structural design of BRBF was varied with regard to building height. That is a 5-story building with a height of 17.5 meters. That is a 10-story building with a height of 35 meters, and that is 20-story building with a height of 70 meters. The variation was opted to determine whether structure that exceed a height limitation can still meet the code requirements under earthquake load. And this is the material specification. The material specification for beams and columns use ASTM A992 grade 50 with a yield stress of 345 megapascal. And the material specification for BRB steel core use ASTM A36 with a yield stress of 262 megapascal. And this is the result of the structural analysis with modal response spectrum analysis, or MRSA. All BRBF structural systems were designed using modal response spectrum analysis. The analysis must be include sufficient modes to obtain combined mass participation of 100% of the structure mass. And the best shear from the analysis was scaled using results from static analysis. The study found that the BRBF structure resists about 98 until 99% of earthquake load, thus clearly indicating them as the lateral resisting system for the structure. And the story drift was evaluated. The green line showed the story drift in the X direction. The blue lines showed the story drift in the Y direction, and the orange line showed the story drift limit. The story drift in the X and Y direction has the same value because the floor plan is symmetrical, and the result found that they did not exceed the story drift limit, and the story drift limit is 2% building height. And these tables are the result of the structural design using modal response spectrum analysis. These are the cross-sectional dimension of braces, beams, and columns for 5-story building. This is for 10-story building, and this is for 20-story building. The demand capacity ratio for all elements meets the requirements of less than 1. And that means all the structural element designs with modal response spectrum analysis are able to resist the load on the structure. This is the results of structural analysis using linear response history analysis. To verify the design, the structure was analyzed by linear response history after being designed with modal response spectrum analysis. Linear response history analysis requires three pairs of earthquake history data, and the earthquake history data must be spectrally matched to the design's response spectra. The earthquake record data used are El Centro, Chichi, and Northridge. The structural response were evaluated for all 3 models, and the story drift is reviewed based on the envelope value. And for the 20-story buildings, the limit was exceeded, but for 5-story buildings and 10-story buildings, they do not exceed the story drift limit. The axial force of brace element with linear response history analysis in the 3 building models is larger when compared with modal response spectrum analysis. And the difference is significant for taller models. And if we checking of the bracing capacity, the axial forces calculated by linear response history analysis do not meet the requirement. That means that the previous braces cross-section design with modal response spectrum analysis must be redesigned using linear response history analysis. And this is the pushover analysis. The performance of the structure was evaluated using pushover analysis. Utilizing the force displacement relationship capacity curve and the demand forces. The structural performance points are obtained from this curve, which is then compared with the structural performance level based on ISCE 4117. The results show that the structural performance of the 3 building models is in the level, and the element performance level at performance point is IO, immediate occupancy until life safety level. And the result about distribution of the plastic L, the brass element heals earlier than the other element, as expected in the design. This is the summary of the structural analysis result. This table can be summarized that all 5-story building, 10-story building, and 20-story building can be designed with modal response spectrum analysis, and the design results have met the requirements of SNE 1726-2019. However, when reviewed with linear response history analysis, the inter-story drift exceeds the drift limit for 20-story building. Moreover, the axial force of the braces has increased, so that the sum of the design section must be redesigned if using linear response history analysis. The analytical results suggest that although all buildings show adequate performance, linear response history analysis is the more conservative approach in designing the BRB models. It's offers advantages for buildings that have a height exceeding the requirement in SNE to ensure that the dimension of the design structure are appropriate and meet the requirement. If you from the results of the pushover analysis, the level of the structural performance for our building is at immediate occupancy level. Sorry. Okay. And it shows that BRBF design using model response spectrum analysis can be used in high-rise buildings because it is satisfactory structural performance even when the building height exceeds the limitation. And this is the conclusion based on the result of numerical study. One, the structural design for the 3 BRBF structural models was conducted using model response spectrum analysis, and all structures meet SNE 1726-2019 requirements. For 20-story model, which exceed the height limitation, meet the requirements in terms of the interstory drift in building that exceed the height limit based on SNE 1726-2019, and larger axial forces for braces. 3. The structure obtained for model response spectrum analysis have adequate performance level, that is immediate occupancy, and no element reaches the collapse prevention condition. The distribution of the plastic hinge in the 3 models has also been as expected. That is, the brace element yields earlier than the other elements. Thus, the BRBF design with MRSA has a good performance and can be utilized even when the height limit is exceeded. And 4, to improve the performance of the structure and obtain design results that meet all the requirements of SNE 1726-2019, BRBF structure with a height exceeding the limit in SNE must be designed with linear response history analysis so that the interstory drift of the structure obtained meets the requirements. That's all for our presentation today, and thank you so much for your attention. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you very much, Dia. And even you still have 5 minutes more to finishing your presentations, but you already finished it before the end of this time allocated. Okay, thank you very much, and give an applause to Dea Yulanita. We still have time to raise questions and answers at the end of this session after all speakers presenting their papers. Now we have the third speaker, titled Hybrid Viscoelastic Damper Using Natural Rubber Compound Waste of the Rubber Tire Crumb with Various Compacted Sand, Iron Sand, Natural Sand, and Silica Sands to Increase Damping Property for Non-Engineered Buildings. Written by Edwin and Professor Henricus Priyo Sulistyo. And this paper will be presented by online. Please, are you there, Edwin?
Yes, Professor. I will share my screen.
Are you with us?
Yes. Can you hear me?
Okay, yes, I hear you.
Okay, I will
You have
present.
20 minutes and
Okay.
now time is yours.
Okay, thank you, Professor Rio Suprabo. Okay. Good afternoon, ladies and gentlemen. First of all, let me thank you all for coming here today. And let me start by introducing myself. My name is Edwin, and I'm a final year civil engineering student at Gajah Mada University. And today, I'm going to present a paper with title Hybrid Viscoelastic Damper using natural rubber compound, waste of rubber tire cram with various compacted sands, iron sand, natural sand, and silica sand to increase damping property. Presentation start with introduction and end with acknowledgements. First is introduction. As we know, Indonesia is located between three major tectonic plates, namely Eurasian plate, Indo-Australian plate, and Pacific plate. And then, based on Badan Meteorologi, Klimatologi, and Geofisika, in 2021, there were 10,570 tectonic earthquakes. Also, based on CNN in 2021, there were 244 earthquakes with a magnitude above 5, and 23 of them were destructive. On the other hand, there was also an environmental problems because of waste of used tires. Based on Badan Pusat Statistik in 2021, there was an increase of 1.9% in the number of motorized vehicles. It shows that the waste of used tires will grow over time. And one of the solution is to use waste of used tires to make waste of rubber tire cram, or we can say WRTC, as a mixture for rubber compound. And on the other hand, many types of sand are available in nature, and we often encounter in life, and it is also easy to obtain. And based on previous researches, their surface frictions may create damping effect when encapsulated by flexible material such as rubber. Next, I will explain about materials and experimental procedure used in this research. The first material was rubber compound that was obtained from Polytechnic ATK Yogyakarta. The main component of this compound was a natural rubber in the form of rib smoke sheets with a mixture of synthetic rubber or styrene butadiene rubber. The second material was WRTC, or waste of rubber tire cram, that was obtained through ambient or grinding process. The grain size obtained for this material was mesh 100 or 0.15 millimeters. Next is natural sand that was obtained from Mount Merapi in Central Java. And the finest modulus of natural sand is 3.034. The second sand that we used was iron sand that was obtained from West Java. Iron sand that was used had uniform grain size of 0.15 millimeters or mesh 100 with finest modulus of 0.0028. And lastly, the material used in this research was silica sand that was obtained from local shop in Yogyakarta. The silica sand had finest modulus of 2.345. And there were 5 mixture variations used in this research, as we can see in the table. R1 or specimen made from rubber compound only, and then R2 or specimen made from mixture of rubber compound with 25% WRTC, and then R3 or specimen R2 with compacted natural sand, and then R4 or specimen R2 with compacted iron sand, and lastly R5 or specimen R2 with compacted silica sand. The one highlighted in blue color is proportions for rubber compound and WRTC, and the one that is highlighted in yellow color is proportions for sand. Before being used to make specimens, natural sand, iron sand, or silica sand are washed and dried in an oven at 110 centigrade for at least 24 hours. 4 pieces of rubber test specimens were made for every mixture variations. For the tensile test and hardness test, the specimens used were R1 and R2 mixture, but for the damping test, the specimens used were ALDE 5 variations. Next is mixing and curing procedure. The first step for mixing and curing procedure was rheology test. Rheology test was used to find optimum time and temperature for the vulcanization process of rubber. And from the rheology test, it was found that the optimum time was 17 minutes and 30 seconds with optimum temperature of 130 centigrade. The next step was mixing rubber compound with 25% WRTC using a 2-roll mill machine. And the mixing process was carried out while controlling the temperature so it didn't get too hot and reach the vulcanization temperature. After that, rubber mold was made and then filled with natural sand, iron sand, or silica sand, and the top side will be covered with a rubber compound, as we can see in the figure. The last step was the vulcanization process using a press machine. The time and temperature used in this vulcanization process was the same that we get from the rheology test. The vulcanization process was done with a temperature of 130 centigrade and time for 17 minutes and 30 seconds. Next is the testing procedure. First is the tensile test, and this is the specimen used for the tensile test. Dumbbell-shaped test specimens was used for tensile test with dimension as shown in the figure. And this is the tensile test configuration. The dumbbell test object was clamped using a grip, and the machine will operate with a nominal speed of 500 millimeters per minute, and the changes in length from grip to grip was observed until the test object breaks. The tensile test was carried out based on SNI ISO 37/2011, and the test was carried out for R1 and R2 specimen. And the equation used to calculate the tensile stress was equation number 1, and the equation used to calculate the strain was equation number 2, and the modulus of elasticity of rubber can be calculated using equation number 4. After the tensile test, there is also hardness test, and this is the hardness test configuration, and this is the specimen used for the testing. For this test, compressive load used for this durometer sort A type is 1 ± 0.1 kilogram, which can measure the depth of penetration with a scale of 0 to 100 in 3 until 15 seconds. There are two types of testing for rubber hardness, durometer test and IRHD test. And durometer test sort A was used in this research to measure the rubber hardness. And the hardness test was carried out based on ISO 7619 2010 standard. After the tensile test and hardness test, there was also damping test. And this is the specimen used for determination of damping ratio, as we can see in the figure. It was made into a model resembling viscoelastic damper using two pieces of rubber specimen with dimension of 100 millimeters times 100 millimeters times 25 millimeters that was glued to the iron plate. And the method used to calculate damping ratio in this research was equivalent viscous damping ratio. The first step was to calculate equivalent stiffness using equation number 4. And then we can calculate the dissipated energy that was the area inside the hysteresis loop. And after that, we can calculate potential energy using equation number 5. And lastly, we can calculate the equivalent viscous damping ratio using equation number 6. The damping test was done using shake table from ANCO engineers with dimension of 1.5 meters times 1.5 meters, and the other specifications can be seen on the slide. Next, we can see the setup used for the damping test. The test was carried out by running a sinusoidal signal on the shake table with a frequency of 0.5 Hertz with various lateral deformations, 4 millimeters, 6 millimeters, 8 millimeters, 10 millimeters, and lastly 15 millimeters. Next is result and discussion. From the hardness test, the results showed that the addition of 25% WRTC caused an increase in the hardness value of the rubber by 11%. Different from the hardness test results, the results in the tensile test showed that the addition of 25% WRTC caused a decrease in the tensile strength by 19%. And this is the results for modulus of elasticity of rubber, where it showed that the addition of 25% WRTC also caused a decrease in the modulus of elasticity by 5%. And next, we will see the results for the damping test. Here, we can see the hysteresis slope graph for R1 specimen, or specimen made from rubber compound only. And next, we can see the graph for R2 specimen, or specimen made from mixture of natural rubber compound with 25% WRTC. And this is the graph for R3 specimen, or R2 specimen with compacted natural sand. And this is the graph for R4 specimen, or R2 specimen with compacted iron sand. And lastly, this is the graph for R5 specimen, or R2 specimen with compacted silica sand. And this is the example of envelope curve for R3 specimen. And this is the envelope curve for the R4 specimen. And this is the envelope curve for the R5 specimen. And from the envelope curve, we can see that as the deformation increase, the stiffness of the rubber decrease while the force increase. It shows that the addition of sand inside the rubber increase the damping ratio as the deformation increase. Next, we can see the equivalent viscous damping ratio results for R1 and R2 specimens. Both specimens showed results ratio results for R2 specimen is slightly better than the R1 specimen. And next, we can also see the R4 specimen and R5 specimen. The results show that the equivalent viscous damping ratio value increase as the deformation increase. This is due to the damping aid through friction between the sand grains. Therefore, it could be seen that the addition of sand has an effect on increasing the damping ratio of rubber. Next is conclusion. There are several conclusions that can be drawn from this research. First, the addition of 25% WRTC decreased the tensile strength and modulus of elasticity of rubber, but it increased hardness and damping ratio of rubber, although not significant. Second, the use of WRTC is also an environmentally friendly solution to help reduce waste tire. Third, the addition of sand can increase damping ratio of rubber. As the deformation increases, the value of damping ratio also increases for test specimens with addition of sand. Fourth, the addition of natural sand, iron sand, or silica sand caused an increase in the damping ratio by 123%, 206%, 141%, respectively at the lateral deformation of 15 millimeters compared to the R1 specimen. And lastly, acknowledgements. We would like to thank you to the Gadjah Mada University Research Directorate for supporting this research through the Final Project Recognition or RTA program. Thank you is also addressed to the workshop of the Polytechnic ATK Yogyakarta for preparing the test specimen, as well as the structure laboratory of Gadjah Mada University and the Laboratory Center for Rubber, Leather, and Plastic Tests of the Special Region of Yogyakarta for letting us to test those rubber properties. And that's all for me. Thank you so much for your attention.
Thank you, Edwin. Applause for Edwin. Congratulations for your innovations about rubber clamp damper. Very good, Edwin.
Thank you, Professor.
Okay, the next speaker. The next speaker is Muhammad Rizaldi. Are you there?
Yes. Can you hear my voice?
Yes, I hear you. Okay. Muhammad Rizaldi will present the paper titled Seismic Load Design of Ruko Dam Suppletion Tunnel PD Regency Aceh, Indonesia, based on deterministic and probabilistic seismic hazard analysis. Time is yours, Rizaldi.
Okay. Thank you for the time, Prof. Priyo Subroko. Good afternoon, all participants of 5th International Conference on Earthquake Engineering and Disaster Mitigation. First of all, I would like to introduce myself. My name is Muhammad Rizaldi Nur Aulia. I'm a master student at Geological Engineering Department, Gadjah Mada University. As a first author, and Dr. Igede Budi Indrawan and Dr. Fahmi Aldiamar as a co-author, also my supervisor. Today, I would like to present my research entitled Seismic Load Design of Rukoh Dam Suppletion Tunnel in PD Regency, Aceh, Indonesia, based on deterministic and probabilistic seismic hazard analysis. Today, outline first is introduction, and then a study area. The third is methodology. Fourth is earthquake data. Fifth is ground motion prediction equation. Next is logic tree frameworks, and then earthquake scenarios, and then peak ground acceleration calculations and response spectra, and probabilistic seismic hazard analysis, and the last is conclusion. The first one, introduction. Since damage such structures cause significant financial loss and environmental risk, monitoring seismic risk at key infrastructure location, including dams, tunnels, and other infrastructure, is essential in earthquake engineering. As you can see, the picture is PD Jaya earthquake in 2016 is located near the study area. And then two well-known methods for measuring seismic hazard are deterministic seismic hazard analysis and probabilistic seismic hazard analysis. Both techniques follow a four-step procedure, with the first two phases being identical. The study area, the research location is in the Rukoh Dam Suppletion Tunnel, which is administratively located in Pantuan Bunut Village, Tirus District, PD Regency, Aceh Province, Indonesia. Geographically, it is situated in northern part of Aceh Mountainous Block, as you can see indicated in the green dots in the map. The lithological group of the area is dominated by middle to late Miocene mudstone and calcareous siltstone from the Kota Bakti formation. Seismotectonically, the construction site of the suppletion tunnels area falls in the Sumatran Fault Zone, especially in Selimum South segment. The distance between the location and the Selimum South segment is 6.03 kilometers based on surface projection. Based on the code of SNI 72026 2019, 10 kilometers or less than of an active fault projection capable of producing magnitude more than 6 or greater earthquakes, it needed to be done site-specific response analysis. So that's why the reason we need to do site-specific response analysis. The next, the methodology. First, deterministic method evaluates the downshaking hazard based on controlling source, which is considered to provide the greatest threat among all the potential sources at each given position. Locating and identifying all earthquake source in a place that might cause considerable ground motion is crucial. The deterministic approach is then used to determine the distance that is closest between the earthquake source zone and the study site. The distance used could either be the distance from the epicenter or the distance from the hypocenter, depending on the empirical equation that is employed. By choosing a controlling earthquake that is expected to cause the greatest shock by comparing the magnitude of the shock produced by the earthquake at a certain distance and location, applying one or more ground motion parameters derived from empirical equation are utilized to explain these properties. Peak acceleration, peak velocity, and response spectrum ordinance provide an estimation of the parameters of the earthquake hazard. The earthquake data, there are 23 active faults that have been identified by previous researcher at Pusat Studi Gempa Nasional at 2017 near the site location. You can see, as you can see in the previous figure at the study area, it is the map. It is the type and deep, length, magnitude, maximum magnitude, and slip rate for each fault that have been identified. Most of the active faults have a trend to northwest to southeast because of the Indo-Australian plate subductor erosion plate from the southwest to northeast produce many faults that have trend northwest to southeast. The fault that related and near to site location is Sumatran fault, Selimum South segment that has type and mechanism of strike slip fault, and the depth of fault is about 90 degrees, and the length of fault around 38 kilometers, and the magnitude maximum that ever recorded was 9.6 magnitude moment, and the slip rate was 8 millimeters per year. The ground motion equation that we used in this study, the first equation was Burr and Atkinson, NGA 2014. This is equation developed as part of the NGA West 2 project. The data that been used to develop the equation consists of background acceleration and velocity, as well as 5% pseudo-spectral acceleration for periods ranging from 0.01 second to 10 seconds. These equations are generally applicable for earthquake of 3.0 to 8.5 magnitude moment, except of constraint for magnitude moment greater than 7 for normal slip events at distance from 0 to 400 kilometers. At sites having shear wave velocity of PS30 in the range of 150 meters per second to 500 meters per second, and for spectral periods of 0.01 to 10 seconds. And the basin depth Z1 are 0 to 3 kilometers, and CL1 and CL2 event types are main shock and aftershock. The second equation that used in the study was Campbell-Bolzognia NGA 2014. This equation developed also as a part of NGA West project. This ground motion prediction equation is considered to supersede their previous NGA ground motion model for peak ground acceleration and peak ground velocity, and 5% damp linear pseudo absolute acceleration response spectral ordinates. This ground motion is considered to be valid for estimating peak ground motion and response spectral ordinates for shallow continental earthquakes in active tectonic regimes, for which the following general apply, such as magnitude moment greater than 3.3 for California region, or magnitude moment greater than or equal to 5.5 globally, and the closest distance to the fault rupture plane is 0 to 300 kilometers, and the shear wave velocity of PS30 is from 150 to 1,500 millimeters per second, corresponding to an NAHRP site categories B, C, D, and E. The sediment depths of sediment depths are 0 to 10 kilometers, and the depth of top of fault rupture plane is 0 to 20 kilometers, and the hypocentral depths are 0 to 20 kilometers, and the fault rupture plane depths are from 15 to 90 degrees. The third equation that uses was Young's NGA 2014. This equation developed also as part of NGA Wtih project. This equation represents an update of the 2008 ground motion prediction equation, or peak ground acceleration, peak ground velocity, and 5% damp pseudo spectral acceleration. This update was based on analysis of a greatly expanded ground motion database and an extensive set of ground motion simulation. This equation generally applicable or predicting horizontal ground motion amplitudes for earthquake in active tectonic regions, which is following condition: the magnitude moment greater than or equal to 3.5 and less than or equal to 8.5 for strike slip earthquakes. Magnitude moment greater than or equal to 3.5 less than or equal to 8 for reverse and normal faulting earthquakes. The depth of the top of fault rupture plane less than or equal to 20 kilometers, and the closest distance to the fault rupture plane are greater than or equal to 0 kilometers and less than or equal to 300 kilometers. And the shear wave velocity of PS30 are greater than or equal to 180 meters per second and less than or equal to 1,500 meters per second. Next is logic tree framework. The weighting of each parameter calculation function is determined before the logic tree function output is assigned, particularly weight. The weighted value represents the amount of confidence in the parameters in question. The final result, which is the total different weight value, may be calculated using the weight value. When all parameters are added together, a value of 1 is achieved. The final result is calculated by adding the weight of each parameter. As an example, from the earthquake data, Selimum South segment of Sumatra fault zone has 9.5 magnitude moment based on characteristic fault models. By adding slip rate as a parameter, the weighting of magnitude magnitude uncertainty is
Rizaldi, are you with us? Rizaldi, are you with us? This connection is lost. Okay.
Yes.
Are you there?
Yes, I'm here. Can I continue?
Okay.
Yeah, these are the earthquake scenarios based on the characteristic fault models. And this is the earthquake scenario based on Gutenberg-Richter criteria of activity value. The probabilistic seismic hazard analysis that I used in this study was from Pusat Studi Gempa Nasional, provided in the Source and Seismic Hazard Map 2010 17 is the PGA, short-term spectral acceleration at period 0.2 second and spectral acceleration and period 1 second. The peak down
have 3 minutes, Rizaldi.
Yes,
3 minutes.
Thank you.
More.
Okay. The peak down acceleration calculation, the deterministic seismic hazard analysis was conducted using hazard average software, and based on the Bohr-Atkinson et GA 2014, the PGA is 0.59 and the spectral acceleration at period 0.2 is 1.44 and the S1 is 0.59. And based on Campbell Bozognia, it has a larger value of the PGA of 0.873 and the SS is 1.0707 and the S1 is 0.61. And the Chioyong's NGA 2014, the PGA was 0.6 and the SS is 1.55 and S1 is 0.52. And also we compare the probabilistic and deterministic seismic hazard analysis that have been compared to. The probabilistic method has a PGA value of 0.537 and it's as 1.291 and S1 is 0.575, which is has a deterministic method has a bigger value than probabilistic method. This is the response spectra of each ground motion equation prediction and the probabilistic method and deterministic method. And the conclusion was the results are given in terms of spectrum acceleration, which show the variance of maximum PGA based on several ground motion prediction equation. The value PGA value is 0.66 G according to deterministic method as compared to the calculation with probabilistic method of 0.537 G. And this is because the method, the deterministic method always consider the worst case scenario of earthquake event, while probabilistic method will yield a lower value because of the uncertainty surrounding the possibility of an earthquake. Until now, no one has been able to determine when an earthquake will occur. We can only predict earthquake behavior based on the past event, so it's better to prepare for the worst than to cause a lot of loss and life. I would like to thank you to Implementation Unit for Geotechnics, Tunnel and Structures, Directorate General of Highways, Ministry of Public Works and Housing, for the use of exact software. Thank you for this from me. Thank you for your attention.
Thank you very much, Rizaldi. Ladies and gentlemen, it's come with the question and answer session. Please, if you have questions, okay, Professor Bambang, Erwin, and Andre. Yes, Andre. Okay. Pak Yosua. For all four presenters, please mention the question Professor Bambang or first? Professor Bambang Zendra first.
At the time, my question is to Mas Asdam, the first presenter. I have two questions or clarification. The first one is related to the model. Model. You have a beam column join model. The first model made from C. Okay, and then you show to us that you compare the result of cyclic loading in that figure. My question is there any cracks developed on the CEE model, beam column joint made from CEE model? ECC, sorry, ECC. At the end of the test, because the slide that you showed to us, we could not see what is the final result of the test in terms of the cracks. And if it is cracked there, what is the comparison between the width of the crack, maybe the number and also the pattern of the crack, if we compare from the normal concrete and the CC concrete? Whether you include the reinforcement or not in the finite element model. Thank you, Prof. Ria.
Okay. Please, Mas Asdam.
From Sandro for the excellent questions. I'm going to answer the first one. So when we did the test, so basically we have 4 specimens, only 2 specimens for direct use to the direct comparison between normal concrete and ECC specimens. At the end of the test, we see different crack patterns, both in concrete and in ECC. In concrete specimen, the crack mainly occurs at the interface in the beam column joint and also extended towards the joint core. So we have some diagonal cracks in the joint core. But in ECC, at the end of the test, we see some big opening cracks, localized cracks at the interface only, something like that. It's towards the plastic region of the beams. For the second questions about the model, because we adopted 3D modeling, so we use discrete representation for the rebar. So it's not smeared, but followed what we did during casting. But for the concrete, we use fixed smeared concrete model, something like that. Yeah. I hope it answers all the questions that you raised.
Thank you very much, Mas Asdam. Okay, the second one, Erwin.
Okay, thank you, Pak Prabowo. My name is Erwin, and I would like to ask Edwin.
Edwin, are you there?
Yes, I'm here.
Okay.
Okay.
This is Erwin.
So, Mas Edwin, first of all, congratulations on your systematic and clear presentation.
Yeah.
Secondly, my question is, in R3, R4, and R5 specimens, where you have a sand infill specimen, the last cycles, the last drift ratio at 15 millimeter, I think, I see some degradation for the second, third, and fourth cycles. Could you explain more what causes those degradation and how it might impact our behavior? Thank you.
Okay. Thank you for the question, Mr. Erwin. Okay, so my answer is, as I showed before, the rubber specimen were glued to the iron plate. And the glue that we used was called vulcanizing method, where the adhesive layer we use some called vulcanizing method. So when we test at the lateral deformation of 15 millimeters, we saw some the adhesive layer has started to come off. So maybe it results in some deformation at the third and fourth hysteresis loop. Maybe that's my answer.
Yes, thank you.
Thank you.
Thank you very much. Next.
Check. Okay. Okay. My name is Andre, and I have also two questions for Mr. Asdam. Yeah. Then of the mixture, what is the volumetric ratio of steel fibers that you use in your mixture, and is there any issue with the workability? And also, is there any issue with the randomness of the fiber orientation? That was my first question. And my second question was related to the crack pattern as well. If I remember correctly, when you show the crack formation in your simulation, it seems that there is a larger crack actually farther from the column for the ECT and the normal concrete. So you shifted the plastic hinge region. And is there any concern about that? Thank you very much.
Okay, so on research yet a lot. So regarding your cement and also fly ash and fiber, and the fiber is quite small, so typical of human hair, and we added 2% by volume, something like that. And about the consistency of or workability, it is more like the SCC. So instead of like using the slump test analysis testing, we use slump flow. So there's nothing more challenging about the dispersion of the fiber. So it's quite easy compared to the SFRC that we fabricated. And what was your second question?
Yes, my second question is related to the result.
The cracks.
Yes, your simulation shows that there is a larger.
The simulation that I showed earlier was under development. So I'm not saying that it's the final version, because at the moment we are currently developing the reliable consistent model for ECC, starting from the shear panel test, something like that. Because what we need to pay attention to address that, we can see some big cracks at the joint, more like that I showed earlier. So it's not the final model. So maybe if you can bear with me, we can finalize this and then I will let you know.
Yeah, thank you very much.
Thank you, Mas Andre. And now, Pak Yuswan, please.
Thank you, Pak Prabowo. My name is Josia, and I want to ask to the first Mas Asdam. Mas Asdam. Yeah, I'm interested with the tools. If I'm not mistaken, you're using DIC, right?
Yes.
Digital image correlation. Yeah. Did you make a comparison between the result from the DIC and maybe you put some dials or LVDT, and how is the precision of this DIC? And the second is, if I'm not mistaken, you did the experiment in the lab, right? Can you also use the DIC outside? And how long is the distance between the camera and the sample? And if I'm not mistaken, because I see in your presentation, you use a normal camera, and did you use special tools like a heavy tripod? Because if the camera move a little, it will. So if you use it outside the building, can it produce a perfect picture like that? Thank you.
Well, thank you. Very interesting question. So I can confirm that we have done some measurement outside the laboratory. So when I was there, we did some testing. So basically, we tested and we implemented the DIC outside the laboratory. So regarding the focal length of the camera and the surface of the region of interest that we concern to the DIC capture the phenomenon of cracks. So it actually depends on how large your region of interest. If it is larger enough, then you have to move away your camera. But the concern is the pattern that we apply on the surface. So it is depending on the size of the region of interest. So if you use like very small dots, then your camera cannot capture the movement of the dots or the pattern. So basically, you have to try first and then try to compare with the actual cracks when it occurs. So, but the possibility is there. So yeah, don't worry. And for the experiment in this specific experiment, so we did about the result from the DIC and then the assessment, but we did not present here at the moment. It's on another publication that we planned to publish. But if you want to see about the verification that we have done, there was one paper that we have published, but it's not in the beam column join, rather it's in the 4-point bending test of the beam. So you can like see what we did there. Thank you.
Thank you.
Okay, thank you very much. Is there any questions from the audience online? Well,
yes. Check.
Please.
Check.
Oh yeah. Please mention your name and the question to address to.
Okay, thank you, Professor. So my name is Benny. I'm from Universitas Gadjah Mada. I would like to ask a question for the last presenter, Mr. Muhammad.
To Rizaldi, okay.
Yes, Professor. So my question is, well, first of all, it was a nice presentation and an interesting topic. I would like to ask about the methodology that you use. Why did you use the ground motion prediction equation? You did like 3 equations. If I'm not mistaken, it was Bohr, Atkinson, Campbell, Wozornia, and Xiao-Yang's. Why did you choose these 3 questions? Thank you.
Rizaldi, are you with us?
Yes. Yes. Thank you, Mr. Benny, for the question. The first, why I'm using these 3 equations. The first, because these 3 equation specifically used the data from a shallow crustal earthquake, which is very suitable for research location because my research location only have 6.03 kilometers surface projection from Selimum South segment of Sumatran fault zone. There is also that fault is shallow coastal earthquake from previous researchers that have been identified. And second, this equation also used in the making of seismic source and hazard map 2017 by Pusat Studi Gempa Nasional for probabilistic seismic hazard analysis. So this is so it's fair enough to compare the deterministic seismic hazard analysis and the probabilistic seismic hazard analysis with the same equation. That's all from me, Mr. Bin.
Thank you, Mr. Muhammad, for the question, for your answer.
Jadi sebenarnya lebih bagus, Pak.
Okay, thank you. I think the time is there any one more? Okay, please. Your name and your questions.
Thank you, Prof, for the opportunity. My sound is clear?
Okay.
Okay. My name is Clarino Tefle Stuart Armando Galak. I'm from Gajah Mada University, and I want to ask to the last presenter, Mr. Muhammad. It's related with the previous question from the other questioner. It's about first is what's your objective to this study, and the second, why do you need to compare between DHA, deterministic seismic hazard analysis, and PHHA, probabilistic seismic hazard analysis, to design your seismic load? It's only two of that. Thank you, Prof.
Okay, thank you. Rizaldi, are you with us?
Yes.
Okay.
Thank you, Mr. Clarino, for the question. First of all, the objective of this study was to design a seismic load due to the excavation and the construction of the Dam Suppletion Tunnel. Because, as I said before to Mr. Beni also, the site location have 6.03 kilometers surface projection from Selimum South segment of Sumatran fault zone. So that's why I need to design the seismic load in case there's a great or big earthquake source from the Selimum South segment Sumatran fault zone. So, and last is for the research. I also want to compare the DSHA and PSHA on stability of support system Dam Suppletion Tunnel. So it is still ongoing, but it is crucial to do the seismic load design first. So that's all from Mr. Clarino. Thank you.
Is that all, Rizaldi? Okay. Okay, ladies and gentlemen, we come to the end. The time is up. And please give a big applause to all presenters. Yeah. And thank you very much for all participants, all speakers for the sessions. And now we come to coffee break. And we have a 20 minutes coffee break before continuing our parallel sessions in this room. Thank you very much and have a good day.
Hello, good morning, everybody. I would like to describe our special buildings, which is called SGLC building, Smart and Green Learning Center.
The SGLC buildings is probably the first building in Indonesia that use a seismic device which is called a viscoelastic damper.
As we know that in Yogyakarta, the earthquake is very high, and we have a potential high earthquake occurring in our frame structure, and we put a seismic device.
Rubber damper have a 40 by 40 centimeter square and 2 centimeter thick. The capacity of the damper is about 40 ton or 400 kilonewton.
Very complex because the behavior is not only depend on the displacement, but also depends on the frequency during the earthquake.
It is divided into groups from the first to the 7th floor. We put 2 sets of seismic device, 3 of them in X direction and another 3 is in Y direction, and another 30 seismic dampers we placed on the 7th floor to 11th floor.
The challenge regarding to the construction of SGLC is related to the preciseness, and the second one is related to the schedule matching, because the damper holder is prepared in Indonesia while the damper itself produced in Japan.
This damper are designed to reduce lateral displacement, so that the interstory drift should be less than 1%. These dampers, if we don't use this damper, so the lateral interstory drift will be up to 2%.
When the earthquake entering our structure, the energy has been reduced, maybe up to 60 or 70%. And that's why the effect of earthquake on our building will be much better.
So we hope that using these dampers more comfort.
In this case, the earthquake energy will entering our building in full capacity. However, at every floor that we have, it will be reduced by the damper.
This building also equipped with 13 accelerometers. There are 3 axis axiometers on pitch or on ground floor, and there are 2 axes in certain floors, so that we can monitor the lateral displacement at any time. So at certain displacement, these accelerometers can alarm, and hopefully that everybody using this building will be more safer for people using these buildings.
We are going to use this seismic. Of course, we should make sure that all the parameters that will be used in the model should comply with the real behavior of the device. Therefore, it is important that the device should be tested before we use it in the model and before we use in the real building.
So we have to consider the situation. Related to the preciseness, we have only 2 millimeter tolerance in order to make the damper work properly. And the second one, related to the construction schedule matching, we have to start the construction, then pack and ship to Indonesia. So in terms to schedule the method, which is we use steel plates in the position of dampers, and then once the damper come to the site, we will release the dummy damper and then replace with the original ones.
There are 2 objectives of testing this device in the laboratory. The first one is we are going to find out the proper parameters to be used in the modeling. And the second one, we need to make sure that the behavior of this device satisfy the code.
So this kind of method is actually really interesting, because we have to check the preciseness of production in Indonesia to match the standard production from the damper production in Japan. The second one, we have to match about the scheduling, how to maintain the progress and the sequence to the arrival of the damper from Japan.
In SNE 2019, this device is categorized in chapter 13 about dampers. And it is said in the code that before we use this device, we should carry out laboratory tests to check the behavior of this device, whether it is satisfied or not.
So I think in terms of the use of the damper, this is the 2 aspects that we have to really concern. Number 1 is related to the construction method, preciseness, and then the second one is how to match with the schedule matching. Construction become more challenging, and we are very thankful to all parties, from the consultant, the producer, and the contractor, to make the construction. And like to promote the use of this kind of application of its kind in Indonesia, and this kind of damper is not only for new building, but also it's very, I think, good opportunities to implement in the existing building.
When the earthquake is coming and struck our structure will behave better and better, not only at one earthquake, but it should be at every earthquake that we have in the future.
In order to retrofit all the seismically improve the performance of existing buildings. So we do hope that the use of damper system of its kind, which is made of viscoelastic high rubber damper, is become more engineering communities, and at the time probably we can use it in more kind of construction, both for new building or for existing building for seismical improvements. Thank you.
Indonesia experiences frequent earthquakes due to its position on the Pacific Ring of Fire, an arch of intense seismic activity where tectonic plates collide. It stretches from Japan through Southeast Asia and across the Pacific Basin. Earthquakes are one of the biggest threats to Indonesia in terms of natural disaster, as they often strike in populous areas such as the bigger cities, making many people lose their life, homes, and property. According to the USGS, earthquakes with a magnitude of around 5 on the Richter scale occur almost daily in Indonesia, but often with little to no damage. More devastating earthquakes are the ones with a magnitude above 6 on the Richter scale. The great degree of material damage is exacerbated by the poor state of the country's infrastructure, which only increases the devastating consequences of earthquake. There are some great earthquakes that occurred in Indonesia. 9.3 on the Richter scale earthquake occurred on December 2004 in Aceh. An earthquake with the same amount of Richter scale also happened in Nias on March 2005. Around 160,000 people lose their life. There are also another earthquakes that take place in Indonesia. On 27 May 2006, an earthquake occurred in Yogyakarta and its surroundings area, such as the district of Bantul, Klaten, Gunung Kidul, and Kulon Progo. The 2006 Yogyakarta earthquake, also known as the Bantul earthquake, occurred at 5 a.m. with an epicenter position of 7.97 degree south latitude and 110.44 degree east longitude, a depth of 10 km, and a moment of magnitude 6.3. The epicenter of the earthquake was located about 6 km from the coast at a depth of 35 km in the South Sea, and the maximum MSK intensity was 8. This earthquake shocked the coastal area of Parangtritis, Baron, Samas, Blagah, Wonosari, Gunung Kidul, located in Ring 1, followed by Bantul, Kulon Progo, and Klaten district in Ring 2. Other DIY areas were also shaken from the Keraton, Sapen to Kaliurang areas. The earthquake was even felt as far as Purwokerto, Magelang, and Purbalingga, Central Java. The earthquake caused damage to people's homes and public facilities. The area that was most severely affected after the earthquake did not occur in Ring 1, but in Bantul Regency, which is located in Ring 2, with the largest concentration of losses in Bangbang Dipuro sub-district, followed by Imogiri, Pleret, Piungan, and Sewon. The Bantul area has an alluvial soil structure which caused severe devastation after the earthquake. Overall, the earthquake resulted in more than 5,800 people being killed, 120,000 of buildings destroyed, and financial losses of 29.1 trillion rupiah or 3.1 billion US dollar. The government immediately responded to this condition with more speed in responding to the post-tsunami disaster in Aceh at the end of 2004.
Construction company?
Infrastructure?
Well, you're not wrong. But it goes beyond your imagination. Here's a story you have never heard before. The world's business has changed since the pandemic, but our company experienced a tremendous change to keep growing. We are more than just a construction company. See this beautiful property? Fascinating, isn't it? For each of our customers. Passionately, that could improve connectivity, efficiency, and ease of access for citizens' lives. And that's not all. We do much more.
Dari Banda Aceh ke Sigli, itu sudah 86%, ini cepat sekali.
merupakan tahun penuh tantangan, seiring dengan munculnya varian baru COVID-19 yang membawa dampak signifikan bagi pergerakan ekonomi nasional. Meski demikian, Wika beton terobosan yang tepat untuk menghadapi berbagai dinamika di sepanjang tahun 2021. Pionir produksi beton pracetak di Indonesia sejak tahun Wika Beton melakukan aksi korporasi sehingga resmi menjadi perusahaan menetapkan tujuan bisnisnya. Wika Beton menetapkan visi untuk menjadi perusahaan terkemuka dalam bidang engineering, production, installation, industri beton di Asia Tenggara. Untuk mengimbangi dinamika bisnis yang terus berubah, Wika Beton melakukan sejumlah transformasi nilai-nilai budaya perusahaan. Dan saat ini, akhlak menjadi pondasi nilai-nilai budaya yang ditanamkan oleh setiap insan Wika Beton. Sejalan dengan visinya untuk mempertahankan posisi sebagai produsen beton pracetak terbesar di Indonesia, Wika Beton mengoperasikan 14 pabrik, 1 mobile plant, 6 wilayah penjualan, 5 quarry dan crushing plant. Dalam rangka memperluas pangsa pasar, Wika Beton mendirikan 3 anak perusahaan dan 1 perusahaan asosiasi. Wika Beton tumbuh dan berkembang dengan produk unggulan yang dihasilkan antara lain produk sentrifugal, produk non-sentrifugal, ready mix konkret. Demi menunjang operasi bisnisnya, Wika Beton menyediakan jasa layanan penunjang, diantaranya pemancangan, launching gantry, post-tension, WB SHMS. Meski pandemi COVID-19 masih meninggalkan dampak yang terasa hingga penghujung tahun 2021, Wika Beton mampu mencatatkan kinerja positif dengan carryover 1,45 triliun rupiah, omset kontrak baru 5,21 triliun rupiah, omset kontrak dihadapi 6,67 triliun rupiah, omset penjualan 4,31 triliun rupiah, laba setelah pajak 81,43 miliar rupiah. Secara aktif, Wika Beton tetap berkontribusi pada sejumlah proyek pembangunan infrastruktur tanah air, antara lain Giant Seaworld, Jakarta International Stadium, kereta cepat Jakarta-Bandung, pengaman muara sungai Bogowonto, tol Cisumdawu, proyek signaling Mojokerto. Seluruh proses bisnis Wika Beton dilaksanakan dengan memperhatikan berbagai nilai keberlanjutan demi mencapai efisiensi, konsistensi mutu, mencapai keselamatan dan kesehatan kerja, serta operasi yang berwawasan lingkungan. Pengakuan stakeholders atas komitmen Wika Beton dalam menghasilkan produk dengan standar internasional, konsistensi dalam inovasi dan kualitas, serta kinerja lingkungan sosial dan tata kelola perusahaan dibuktikan dengan berbagai penghargaan yang diterima oleh Wika Beton. Dengan berbagai potensi dan sumber daya, Wika Beton siap untuk tetap
Good afternoon, ladies and gentlemen.
Now we come to the afternoon session, and the first presenter is Mr. Christophorus Alvin with the title of Pushover Analysis in Slab-on-Piles Bridge using Reinforced Concrete Filled Spoon Pile. Mr. Christophorus, the time is yours. You have 20 minutes until 15:52.
Okay, thank you for the opportunity that is given to me. Good afternoon, ladies and gentlemen. At this moment, I would like to talk to you about pushover analysis in slab-on-piles bridge using reinforced concrete filled spoon pile. First of all, let me introduce our team. My name is Christophorus Alvin Slametriono, and my partners in this team is Mr. Iman Satyarno, Mr. Angga Fajar Setiawan, and Mr. Ali Awaludin. I will divide my presentation into 5 sections. I will start with an introduction, and then I will talk about the theoretical background. Then I will talk about the research methodology that is used in this study. And the next, I will talk about the result. And the last one is the conclusion. Okay. The slab-on-piles bridge is one of railway bridge structure type that is currently being developed in Indonesia. There are several railway bridge structure that use this structure type, such as Soekarno-Hatta International Airport Railway Bridge, Adi Sumarmo International Airport Railway Bridge, and also Yogyakarta International Airport Railway Bridge. The structure type consists of 3 main components. These are the slab, the pile head, and the spoon pile. The structure type also has some advantages. The first is more stable for roads that are built in above of the water saturated soil, because it uses spoon pile that is penetrate into certain depth of soil to hard soil. And second is the quality is more guaranteed because it is produced at the factory. The third is the construction time is faster. And the fourth, cost for the maintenance and also for the construction is more efficient. The problem is that the construction of slab-on-piles bridge structure in a
recording in progress,
because the structure is prone to the earthquake loads. And as we know, Indonesia is very prone to earthquakes. On the other hand, previous studies conclude that the failure pattern of a spoon pile with a hole in the center, or we can call it a hollow spoon pile, as a result of earthquake loads is in the form of brittle failure. The initial failure occurred due to an explosion on the inner surface of the hollow spoon pile or the surface of the hole. Therefore, several methods has been studied to increase the ductility of a slab-on-pile structure, like the application of shear panel damper system, the use of composite steel pipes, and the use of method where the spoon pile is infilled with the concrete. And the study is investigate the last method, the spoon pile concrete infilling. This type of spoon pile, where the hollow section is filled with concrete and normal reinforcements, will be called reinforced concrete filled spoon pile, or RCFSP. This is the cross-sectional comparison of the hollow spoon pile or SP and the RCF-SP. A recent study has been conducted to investigate the flexural behavior of a spoon pile with concrete infill. And the experimental research shows that infilled concrete increased the cracking moment resistance and increased the ductility of spoon pile by 38%. Then this type of spoon pile, RCF-SP, is used in this study as a support pier of a railway bridge structure that use slab-on pile structure type. Then the performance-based design. Performance-based design is based on the understanding that the performance of a structure can be predicted and evaluated properly and measurably, so that in the planning process it can provide certainty of performance targets regarding the design structure. And the performance-based design can be done by the various nonlinear analysis, including the static and dynamic method. In the static method is also called the pushover analysis. Based on LEC40, pushover analysis can be done by the capacity spectrum method. The capacity spectrum method shows a graphical representation of force and displacement curve, which is then compared with the demand spectrum. There are two main important things in this method. These are the capacity and the demand. Capacity is the structural ability to resist the demand of crack load, and this depends on the strength and the deformation ability of its component of the structure. And then the demand spectrum is the earthquake load that applied in this graph in the form of elastic response spectrum at a 5% damping. The two spectrum, the capacity and the demand spectrum, is depicted in a single graph, like we can see in the figure on the left side. To find the performance point. The performance point is the intersection of the capacity spectrum and the appropriate demand spectrum. Meanwhile, in the FEMA 356, the pushover analysis, especially the nonlinear static pushover analysis, can be done by calculate the target displacement. The target displacement shall be calculated by following this equation after the force displacement curve is obtained. The performance determination of the slab-on-pile bridge structures in this study is based on ASCE 6114 because the structure is similar to the wave structure. The performance is divided into three levels. These are minimal damage or MD, control and repairable damage or CRD, and life safety protection or LSP. This table shows and describes the limit of each strain from the component of slab-on-pile bridge structure for its level of performance. Then we can jump to the research methodology. The study starts with a preliminary design using the linear elastic design method. The structural components we use in the study for the slab-on-pile bridge structures consist of RCF-SP, slab, and pile heads. The pile heads are divided into two groups. The first one is the theta pile head, which is located on the edge of the structure. And second one is L-type pile head, which is located on the center of the structure. And then the slab dimensions are 20 times 10.3 meters, and the free height of RCF-SP we use is 6 meters. Then this table is described the material properties we use for its components. The soil type data is obtained from a standard penetration test. Standard penetration test to 30-meter depth of soil, and based on the calculation, the soil type is classified into soft soil. The fixity depth of 6 meters RCFSP is obtained at 3 meters from the ground level. So the effective length of RCFSP is 9 meters. The earthquake analysis we use in the study is the response spectrum analysis. The response spectrum design is constructed based on Indonesia National Standard, or SNI 2830-2016, where the location of the bridge is in Aceh, Indonesia. Linear elastic bridge design is carried out with a response modification factor, or R, of 3.5. This is the design result of linear elastic design, or preliminary design, that we did on this study. And the number of RCFSP needed in one bridge segment is 25 pieces RCFSP that are divided into 5 groups, and each group is consists of 5 RCFSP. After that, we can jump to the next part of this analysis, and the next is nonlinear static pushover analysis. The first step we use in this analysis is the determination of plastic hinge properties. The plastic hinge properties in the study are assumed to be located only at the top, only at the points where the maximum moment occurs. So the plastic hinges are located at the top and the fixity point of each RCFSP. The plastic hinge properties are defined in the form of moment curvature diagram. Moment curvature diagram calculations are carried out under considerations of axial load that consist of structural dead load, additional dead load, and half of life load. And then after the moment curvature diagram is obtained, we can run the nonlinear pushover analysis. In this nonlinear pushover analysis, unit lateral loads are assigned at all top nodes of the RCFSP to perform the pushover analysis in the longitudinal and transversal directions. The nonlinear geometric parameter, or P delta, is applied, and the pushover analysis is performed until the monitored displacement is reached the displacement control, where the displacement control is a 5% drift ratio of the effective length of RCFSP. And in this analysis, ADC 40 and FEMA 356 are used as a reference for the nonlinear static pushover method. And then we can jump to the result of the study. First of all, this is the axial load that occurs on each RCFSP after the axial load is applied. The axial load is then applied to the moment curvature diagram calculation. Plastic hinge length we use in the study is half of D, where D is the diameter of the RCFSP. And since the diameter of RCFSP is 0.6 meters, the plastic hinge length is 0.3 meters. Then in this figure are just the moment curvature diagram results on its axial load. And from this figure, we can see that on lower axial load conditions, the ductility is higher, but the flexural strength is lower. And then the moment curvature diagram is applied on every plastic hinge that I was mentioned before, that the plastic hinge at the top is located on the connectivity between RCFSP and pilehead, and the in-ground hinge is located on the fixity point of RCFSP. This is the result of nonlinear static pushover analysis. On the left side, we can see the result from ATC 40. Based on ATC 40 method, the performance point of the structure pushover analysis, but in the longitudinal and transversal directions could not be found because there is no intersection between the capacity spectrum and the demand spectrum. The result is validated with the result from FIMA 356 method, where the target displacement both on longitudinal and transversal directions could not be reached by the structural capacity. All of these results indicate that the structural capacity is not sufficient to resist the design earthquake load. This result condition is not in accordance with the result of the linear elastic design that we did before, where the design has considered the earthquake load. And why does this happen? After being reviewed, the R value is determined because the value of R is 3.5. The R value is determined at 3.5 because it assumes before that the bridge structure with RCFSP has higher ductility, but in fact the ductility of the structure is lower. So we need to redesign the structure with a smaller R, and in this case we use the value of 1.5. This is the result after we redesign the structure using R value of 1.5. Because the R value is different, of course the design results is also different. And based on this result, the number of RCFSP needed in one segment of slab-on-pile bridge is 60 pieces of RCFSP that are divided into 5 groups, and each group consists of 12 RCFSP that are arranged into 2 rows, as we can see in the figure on the left above side. And we also do the pushover analysis again for the redesigned structure. Now we can see based on ATC40 method, the performance point could be determined.
3 more minutes.
Okay, thank you. And in the longitudinal direction, we get the displacement at 0.066 meters, and in the transversal direction is 0.062 meters. And based on FIMA 356 method calculation, we can also reach the target displacement by the structural capacity. In the longitudinal direction, we get the target displacement at 0.065 meters, and in the transversal directions, we get target displacement at 0.06 meters. All of these results indicate that now the redesigned structure could resist the design earthquake load. And this table above shows the comparison of performance point and target displacement. We can see that the displacement of the structure after being analyzed with the pushover analysis get the displacement that are similar, but with ATC40 calculation method and FIMA 356 calculation method. And the table below shows the maximum strain that occurs on the plastic hinge of the structure. And we can see from the table that the maximum strain is still at the minimal damage level. And so globally, the redesigned bridge structures are at the condition of minimal damage also. And finally, the conclusion we get from this study is the design of slab-on-pile bridge with RCFSP based on a linear elastic method using an R of 3.5 requires 25 RCFSP for each bridge segment, but this design could not reach a performance point based on a nonlinear static pushover analysis because RCFSP has low ductility. And when the slab-on-pile bridge is redesigned using an R of 1.5, the requirement of RCFSP increased to 60 RCFSP for each peak segment. And the redesigned structure could achieve a performance point at a displacement of 0.066 meters in the longitudinal directions and 0.062 meters in the transversal direction. At these displacements, the performance of the structure is included in the minimal damage level. I think that's all of my presentation. Thank you so much for your attention.
Let's give the big applause to Mr. Christopher. Thank you. The next presenter is this Mr. or Mrs. Arita Asrianur.
Yes, Professor. I'm sorry.
Yes. Okay. Are you there?
Yes, Professor, I'm here.
Oh. Yes. Okay. Could you start your presentation, please? The time is yours. You have 20 minutes.
Yes. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Good afternoon, everyone. My name is Arita Asrianur, and thanks a lot to Professor Adang Surahman as the moderator. Thank you for giving me this opportunity. It is a great honor to me to present the contents of our paper entitled Shear Capacity of Hollow Reinforced Concrete Members Without Stirrups. This paper compiled by my supervisor, Professor Randy Tamrin, Mrs. Sri Hartati Dewi, including me, Arita Asrianur, and Febi Putriyastari, and Professor Zaidir, and Mr. Sabril Haris. And we are from Civil Engineering Department of Andalas University. The contents of this presentation are introduction and experimental setup, and then the analytical study, the theoretical shear capacity, test result and discussion, and then the conclusions. In construction, circular sections are widely used in reinforced concrete structural members because they have many advantages, such as constant moment of inertia and identical strength characteristics in all directions. But sometimes there are hollow in the cross-section of reinforced concrete columns that function as water drainage pipes or electrical installation or other purposes as shown in these figures. And based on the theoretical shear capacity provided in ACI 31H 2019, we can see there are several variables affected to the shear capacity of a reinforced concrete section. They are concrete compressive strength, and the longitudinal reinforcement ratio, and the cross-sectional dimensions. And this page shows the equation for rectangular cross-section and circular cross-section. In equation for circular cross-section, the cross-sectional dimensions are calculated by 0.h square diameter. And this page shows the existing and previous provision for the shear capacity of cross-section with hollow. And we can see that only the two of the previous provision states that the hollow area is limited only 4%. So due to that fact, this topic is still interesting to study. The focus of this study is to determine the effect of hollow in the circular cross-section on the shear capacity of reinforced concrete structural elements. This page shows the specimens tested in this study. The test variable consisted of the longitudinal reinforcement ratio and the cross-section type, that is with and without hollow. We can see the area of hollow section causes a reduction in the cross-sectional area of concrete by 2.32%, which means that the hollow in this specimen is less than 4%, which is below the provisions. As shown in the figure, all of specimens were not reinforced with stirrups. And this table contains the material data for each specimen. The test setup is simply supported beams with 2 concentrated loads. So the internal forces that occur due to loading like this represent the actual internal forces in the building structure. What I mean is the internal force that occurs in the experimental setup is set the same as the internal force that occurs in the actual conditions of the reinforced concrete column as shown in the figure. And next, for the analytical study, the flexural capacity of circular cross-section was calculated based on the fiber element method, which is done by dividing the cross-section and reinforcement into elements, and it was implemented into a computer program. From the test result, it can be reported that the first crack appears in the maximum bending moment zone with an average value of 23 kilonewton. Then, with increasing load, the flexural crack in the flexural zone extends to the shear span with a diagonal cracking mode. So, in these figures, show the crack pattern of the specimens. And it's shown that all of specimens failed in southern shear with wide diagonal cracks as predicted in this study. As we can see in the deflection versus shear force curve of each specimen, that the shear capacity of specimens with hollow section are not so different with that specimens without hollow. And the horizontal line is showing the value of shear concrete strength, which is calculated theoretically and sequentially from the bottom to the top, to showing the smallest to the largest diameter value. And this picture shows the comparison of shear force versus deflection curves between solid and hollow specimen. And this picture also shows the calculated flexural capacity of specimen with fiber element method. And however, due to perimeter shear failure, all of specimens were proven not reach the calculated flexural capacity. And for the last, it can be concluded that all of specimen in this study failed in the shear mode indicated by the occurrence of a sudden wide diagonal crack, and the maximum hollow area stated in the code 4% provides conservative results for the shear strength of hollow reinforced concrete structural elements. And that is all from me. I thank you for your time and attention. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Let's give Miss Arita a big applause. You are very on time. Maybe we can proceed to the next presentation. Will be given by Dr. Angga Fajar. The time is yours. Yes, you can proceed, please.
Okay, thank you. Dear Professor and ladies and gentlemen, good evening or good afternoon. Okay, today I will present of my research with title Analytic Behavior of an Extended Spoon Pile Supporting Bridge Structure Considering Soil Pile Interaction. So, next. Okay, in Indonesia, today spoon pile spotted slab viaduct is commonly used as continuous elevated bridge for the railway or for toll roads. So this structure contains of the slab at the top and then the pile head, also the pile that function as the column, also the foundation. So if in the high seismic region, maybe when the earthquake occur, the column that work as also foundation will resist the lateral force due to earthquake. So it will have the plastic information in the top near to the pile head, also in the soil. So it will make like a double curvature bending moment. Then based on the previous study about the spoon pile, it behave the brittle failure, also low energy dissipation because it achieve pinching hysteresis loop. So not so many energy dissipation can achieve. In the practical, also some academical study, they propose to give the concrete infill, RC concrete infill in the top area, maybe the length about 2 meters or 3 meters to increase the bending moment strength, also the shear strength. Also, according some researchers at previous, they make a numerical model considering soil structure interaction to accommodate the near real behavior of the slab-on-pile structure. And also some researchers do pushover analysis to achieve the performance points of slab-on-pile. However, this study, the current study, did not consider the pre-stressing effect that resulting the pinching hysteresis loop or low energy dissipation. And then at previous study also, the numerical study of the spoon pile model has been conducted by considering pre-stress effect. So it can achieve the good agreement with the experimental result with pinching hysteresis loop. And then also some previous study, there is a comparison between the slab-on pile with the spoon pile and RC structure, reinforced concrete pile or floor pile. And according to the result, we can see that at the left, that is the hysteresis slope of the slab-on pile with spoon pile, and then the right, the B, is the slab-on pile with RC pour pile. And we can see also, based on the pushover analysis and compare the maximum response under nonlinear time history analysis, the RC pour pile less the response. So, it means they have better performance compared to the RC spoon pile. So therefore, nonlinear analysis of the spoon pile spotted slab feedback should consider cell structure, interaction, and pre-stress effect need to be conducted. So this study discuss about the inelastic behavior of extended spoon pile supporting feedback structure considering soil pile interaction. And in the study, nonlinear analysis including static pushover and cyclic loading to be conducted to investigate the moment and curvature, also hysteresis energy dissipation. At first, to make calibration numerical model, we try to make a numerical model to compare with the experiment from Hutchinson 2002. Like this, the extended pile has had 6 times of the diameter with the sand soil. And then here the results. So in the graph A, the experimental result with the black line, and then the numerical result with the red line. Almost could have a good agreement. And then here the numerical model is the freestanding pile without restrained moment because freestanding. And then if we implement in the slab-on pile, in the top pile will restrain moment. So we try to give the restraint moment in the top of pile. So the result is there is a slope in the color of green color. So it have larger lateral strength, of course. And then in this study, we generate one pile from the slab-on pile. So just one pile. It has a head, it's meter, and then the embedded to the soil until 30 meters. We use nonlinear beam element with displacement based element with fiber section, also considering initial stress of the PC bar to consider the pinching effect due to the pre-stress. And then for the soil model, we use the soil spring with Winkler model. We use the PY material model. And also we use the variation of the spoon pile with and without concrete infill. And then also we have additional comparator. It is RC pile, reinforced concrete pile without pre-stress. And also we compare the soil structure interaction model with the only frame element model with some fixity with the depth is 3 meters below the soil surface. So we have model A, B, C, D until F. Also to monitor the limit state of the RC pile or also spoon pile, we control the maximum the strain in maximum outside of diameter. We control following the limits from ASCE 6114 with the criteria minimal damage, control damage, and life safety protection. And here the curvature response of the numerical model, model A, B, C, D. Model A is a spoon pile with soil structure interaction with concrete infill. Model B, spoon pile with soil structure interaction without concrete infill. Model C, model D is spoon pile with infill concrete without soil structure interaction. So we can see that comparison of the model A and model B. This model, the maximum curvature occur at the top of the pile, and then in the plasticing in the soil not so large, but the model B more larger than the model A for the plasticing in the soil, because model A have lateral moment capacity, larger moment capacity in the top pile. And then compared to the model C and D, of course, model C and D, because has restrained moment in the top, also in the bottom with fixed restraint, so it can achieve symmetry curvature. And when we compare to the RC profile, almost the same occurrence for compared to the spoon pile model. However, the plastic information is longer, more distributed. When while the spoon pile more concentrated. Okay, we will skip, maybe too long. Here the comparison of the bending moment diagram between the model A, B, C, and D. Model A achieve larger bending moment than B because in the top pile have concrete infill. And then here we can monitor the comparison of the skeleton curve under pushover analysis. We can see that spoon pile have strike stiffness, almost the crack may be covered by the pre-stress effect, while the RC profile crack occur and then the stiffness decrease in initial. However, when we can look at the post-yield stiffness characteristic, using spoon pile, the drop of the stiffness or the strength degradation occur earlier than the using RC profile. And also when we compare model A and model B, the lateral strength of the using concrete infill slightly larger than the without infill, but no significant, not so significant. And here we can see the characteristic of the hysteresis loop, model A, B, C until F. We can see model A and B almost the same hysteresis loop, not so many different. So the using concrete infill not so significant to improve energy dissipation. While we compare the model C and D, it is used the fixed restraint without soil structure interaction consideration. We can see it is more larger energy dissipation. However, the lateral strength degradation occur earlier because the very rigid, very fixed assumption. while we compare to the hysteresis loop of the RC profile, we can see that the using RC structure can achieve more plumper hysteresis loop. And we can see also with the equal viscous damping ratio. So with the color black, it is the model A, B, and E. It is considering soil structure interaction. It look in the small deformation, the equal viscous damping using the soil structure interaction will larger than the without using soil structure interaction. However, in the larger displacement, the using fixed restraint will achieve larger equal viscous damping because more plumper hysteresis loop. And then compared to the RC profile, the hysteresis loop of the spoon pile is less than the RC profile, maybe less than 10%. But when we use the profile for the without considering soil structure interaction, maybe about 20%. If we consider soil structure interaction, about 13%. Okay. So we can make some conclusion with this study. Using the concrete infill, it can achieve a slightly higher maximum lateral strength than original spoon pile model. And then the larger curvature plasticing occur in the embedded pile with fixed model rather than the SPSI model due to the extremely large stiffness assumption in the base fix rather than the SPSI model due to the localized flash stiffness area. Also, the concrete infill inflict in the longer plastic hinge length than the original spoon pile due to the increase of the stiffness. The force displacement relationship shown that the fixed base model had the higher initial stiffness and maximum force, but the SPSI model had the larger displacement capacity. It means that SPSI increased the structural flexibility to displace laterally. In addition, the more severe pinching effect occur in SPSI models rather than the fixed base model due to the smaller curvature. The fixed base model provide a higher damping and dissipating energy capability than SPSI in the large displacement. Meanwhile, adding the concrete infill was able to generate same capability as the original spoon pile. Compared to the RC pile, the spoon pile was less energy dissipation. Maybe enough for me. Thank you very much.
Let's give Dr. Angga a big applause. Thank you. Now the next presentation will be presented by Bapak Poltakna Baban. And the title is The Merah Putih Bridge Structural Health Monitoring System Records During M5.7 Earthquake. Yes, the time is yours.
Thank you, Professor Ada. Good afternoon, ladies and gentlemen. Participant of ICWBM conference in this room and Zoom as well. It is nice to be here. Thank you for this opportunity. Before we come to my presentation, I would like to introduce myself. My name is Poltakna Baban. I come from PT Struktur Pintar Indonesia and the company dealing with the test and measurement and including development of a structural health monitoring system. Okay, at this moment, I would like to deliver my presentation showing how a structural health monitoring system records the health of the bridge structure affected by the earthquake. I will start my presentation with the introduction why HMS is important. Then I will explain the HMS on the MP bridge, Merah Putih bridge, followed by the earthquake that occurred in the area and its impact on the bridge and how the bridge responded. As an archipelagic country, roads are the main mode of transportation in Indonesia. And of course, bridges have an important role. Indonesia needs a lot of bridges, including long-span bridges to support connectivity between cities and regions in order to boost the economy. We all know very well that the construction of a long bridge is very expensive. So that needed a system to ensure that the safety of the bridge during its service life. And this condition is more critical because Indonesia is located in an earthquake-prone area. Therefore, with the application of this HMS, we can obtain information regarding the performance of the structure from time to time. One of the bridges that have used as HMS is the Merah Putih Bridge. The bridge is located in Ambon, Molucas. It stretches across the Ambon Street or bay, connecting Poka and Galala village. This is a photo of the bridge. To make it easier to explain, I divide into two, the outer and the inner side, where the inner side is closer to the mainland. The length of the bridge is 300 meters, with a main span of 150 meters, and the height is almost 90 meters, and the width of the bridge is 22.5 meters. The pylon is made of concrete, while the girder is made of steel.
Oh, udah ada, Pak.
This is the schematic diagram of the jembatan Merah Putih SHMS, consisting of sensors in the deck, pylons, and data acquisition unit, data interfaces, data processing, and then display to monitor. This is the table shows the type and the number of sensors that totally have 150 pieces sensor. That should be two type of sensor. One is a measure the load, and the other is measure the response of the bridge. This is distribution of sensors, and in some point, like in the middle of the midspan of the bridge, there are some sensor in one point, and it has 24 electromagnetic sensor in the cable out of the total 56 cable. This is the other perspective. Okay. On October 31st, 2017, around about 8:30 p.m., there is a earthquake occurred in Maluku's areas, and the magnitude is about 5.7 Richter scale, and the epicentrums of the earthquake is 46 kilometer west of Ambon, 61 kilometers east of Ambalu, 82 kilometers southwest of Kairatu, 94 kilometers southeast of Namelia, and 94 kilometers southwest of Piru, with a depth of 10 kilometers. And this is the reading of seismic sensor at the foot of the bridge. We can see here that the west-east axis have a 4.85 Richter scale, and north-south axis is 5.01 Richter scale, and for the vertical axis is 3.55 Richter scale. From the CCTV, it can be seen that general condition of the bridge at the time of the earthquake. There were only 2 motorcycles crossing the bridge. This is the cable force recorded by electromagnetic sensor for the inner bay, and this is for the outer bay, and you can see here no cable forces exceeded the set threshold, either for 55% of ultimate forces, and so 45 ultimate forces. This is the deformation. We can see here that in the middle of midspan, a deflection multimeter is installed to determine the bridge vertical displacement, and it can be seen that during the earthquake, the maximum deflection recorded was 47 millimeter, which is below the threshold of 187.5 millimeters. This is a rotation on the top of pylon in inner bay side. This is rotation also on the top of pylon at outer bay side. Okay, the 3-axis tilt meter shows that there is significant rotation was recorded in the pylon during the earthquake. However, the rotation disappeared after the earthquake. This is the strain at the mid of span in the outer bay side, and this one in the inner bay side. The strains recorded by strain gauge at the critical point of the bridge in the middle span, both the inner and outer side appear to have increased but returned to normal after the earthquake. Okay, from this explanation, we can see how the structure respond in the real-time basis based on SHMS, so that we can understand the structural behavior of the bridge before and after the earthquake. The collected data from sensor have been verified with design assumption and specification to determine safety level of the bridge. From this presentation, we can conclude that the seismic sensor installed on the bridge can provide the earthquake force that impact to the bridge. Second, pylon of the bridge experienced the most significant effect due to the earthquake, but the rotation rate from the tilt meter disappeared after the earthquake. Third, due to the earthquake, the vertical deformation of the bridge increased, but the magnitude was not significant. Fourth, the cable force also increasing during the earthquake, but still in acceptable level. And 5, response recorded on the bridge before, during, and after the earthquake showed that the bridge response returned to its pre-earthquake condition. This indicates that the bridge still behaves elastically. 6, the installation of SHMS has proven to show very well how the behavior of the bridge before, during, and after the earthquake occurred. So such a system needs to be installed to the structure, especially for the long span bridge with which has a complex structure. I think that's all the presentation. Thank you for the attention.
Let's give Pak Nababan a big applause. Thank you. Now we have still plenty of time for questions and answers. I cannot see the online participants, but I can see the audience. Maybe I can invite either of you, if there is one, Professor Bambang, Mr. Andri, Dr. Andri, maybe for the first session, 2 participants first.
Okay, thank you very much for the time. My question is to Pak Polta, Pak Polta, the last presenter. Yeah, the Merah Putih, yeah, Merah Putih Bridge is one of our bridges, long span bridges in Indonesia that has been installed structural health monitoring system. The other bridges include the Suramadu, and then Merah Putih, yeah, the second, and then the third we install in Soekarno Bridge, and then also in Musi 4 Bridge, and so on. So my question, Pak Poltak, is there any system how do we maintain the sensor and also periodically calibrate the sensor that we install in so many bridges in such a way that the result of SMS, structural health monitoring, will be accurate and also useful for us. And it is very important because all of the bridge, especially long span bridges, is usually located in the remote area where not easy to be visually inspected, right? So that's why the structural health monitoring system is a kind of a must that we have to install. In the future, we plan to install so many existing bridges as well as also the new bridges in the future. Okay, I think that's the question. Thank you very much.
Okay, Dr. Andri, please.
Okay, thank you very much, Professor Adang Surahman. Yes, my name is Andri, and I have two questions actually for Ms. Arita, the second presenter. My first question is related to the boundary condition of the test setup. You mentioned before that you designed the setup to, let's say, mimic the bending moment and shear for the column in the real buildings, but How about the axial force? Because in rebuilding, if you design a column, you have some compressive axial force. And my first question is, did you consider also the axial force in your test? And the second question is, did you completely remove the stirrups in the region where you have the plastic PVC, or did you apply like a minimum shear reinforcement? Because probably in reality, it's more, let's say, realistic to have a minimum reinforcement ratio. Just to clarify that. Thank you.
Okay, please, Partner Baban, to answer the question. Yes.
Thank you, Professor Bambang. Like other system needs maintenance, and so this is must be come into budget. Yeah. Not only the system itself, but also need manpower. And the system, we know that as the technology become advanced, and the system also must be adapted to the new technology. And the second one is the calibration. Actually, from the manufacturing, there is also calibration for each sensor. But for the whole system need a calibration after the installation, and usually we can make a calibration when there is no load and good weather. I think that's all my answer.
Yes. Okay. Now, please, Ms. Arita, your time to answer Dr. Andri's question. You are still muted.
Yes.
Okay, please.
For the first question, yes, I don't take I don't take the axial load because if we look at the equation or the formula, it can be deleted and not used. So that's why in the equation that I show in the slide, I just use the equation which include the longitudinal reinforcement ratio and the concrete compressive strength and not the axial load. So I remove that the axial load component from that equation, and that is I'm sorry, rumus untuk I think I will say in Indonesian. So jadi rumus untuk persamaan yang tidak menggunakan beban aksial juga ada gitu, dan saya tidak karena saya tidak memakai beban aksial, dan karena studi ini berfokus pada beban lateral saja yang diumpamakan jika seandainya itu terjadi pada struktur kolom begitu. And for the second question, in the study we don't use stirrups because we just want to see the contribution of the concrete shear strength, but not for all all specimen, not tidak untuk sepanjang benda uji begitu, tapi hanya pada bentang just for hanya pada bentang yang ditinjau saja begitu, pada bentang 1 meter yang terdapat di bentang tengah begitu, yang memiliki gaya dalam persis menyerupai gaya dalam yang diterima oleh kolom pada kondisi aktualnya. That's all from me, I think. Thank you.
Okay. I hope there is no foreign participants, so I don't have to translate Ms. Arita's answer.
Sorry.
Yeah, okay. If there is any additional question, whether from offline participants or from online participants, is there any? Maybe the organizer can watch if there is any from online participants. I can watch from offline participants. I believe or I guess there is no more question. Okay, please, Professor Bambang.
Yes, yeah, my question is for the first presenter. I forgot the name.
Mr. Christopher,
yeah, and also maybe to the second, the third presenter.
I think the topic is similar.
Yeah, okay, similar. Yeah, my question is related to what kind of infill concrete you put inside the hole of the spoon pile. If I'm not mistaken, there is a requirement that the infill concrete must be close enough the modulus and also the strength to the spoon pile that we have. So it is around 15% in terms of the modulus or 50% in terms of the strength. Yeah, to make sure that there is no big difference between those two materials in order to convince the interface between the new infill concrete and the spoon pile that we constructed maybe in precast system. Thank you, Mas Angga and Christopher. Thanks a lot.
Will answer the question, Mr. Christopher or Dr. Angga? Okay.
Christopher,
Check. Okay, before I answer, I would like to thanks for the questions to Prof. Bambang Suhendro. And my answer is the infill concrete that I use in this study is a normal concrete and add with normal reinforcement also. And the infill concrete has a property where the compressive strength is 24.9 megapascal, and compared to the pre-stressed concrete in the external section, the spoon pile concrete in the pre-stressed part has compressive strength of 60 megapascal. Yes, 60 or yes, something in 60 megapascal. Okay. Yes.
Okay, thank you.
Yeah, thank you.
Thank you for the question, Prof. Bambang Suhendro. I think it's very important. Maybe we also already it is good news for me. new information from Prof. Bambang Suhendro. Maybe for in this study, we are following some detail engineering design. Usually, the detail engineering design use the ordinary concrete, the compressive strength about 25 MPa. However, this spoon pile, it is high strength concrete, about 54 or 60 MPa. Maybe at the next research, maybe it is very important to check what the effect if the concrete infill compressive strength is too large different, maybe the effect of the elastic modulus or strength, or compressive strength. Thank you very much.
Okay. May I have adding some comment?
Yes.
Yeah, the importance of the requirement is that to avoid suppose we have the same strain, right? Strain, we hope that the strain will be compatible between the new concrete that we filled inside and the outer part of the spoon pile. There will be a big difference in stresses. If the strain is the same, the modulus is high different on the modulus, then they will receive the very different stress level. The smaller modulus will receive the smaller stress, because we have modulus times strain will be in the stresses. The second thing is relative to the shrinkage of the inner concrete. In the long run, maybe the interface between the inner and the outer will be disturbed in the interface zone. That's why the requirement says that in terms of modulus elasticity, it is less than 15%. However, if you use the strength, it's around 50% different. If we took the regular formula, E is equal to for 700 square FC prime, it is close to what we have, the requirement that we have. 15% for the modulus and 50% for the strength and 15% for the modulus. Okay, thank you.
Okay, thank you, Professor.
Okay. Okay. Please, Dr. Andri, we still have time.
Yeah, thank you. Yeah, I also have two questions for Mr. Christophorus. Yeah. So, when you showed the capacity spectrum in your presentation, somehow it looks to me that the behavior is very brittle. So I was wondering, what was the failure mode that you model? Is it due to the crushing of concrete or something else? And then you propose that in order to achieve the performance point, you want to reduce the R from 3.5, I think, to 1.5. And in reality, it will be very non-economical to do that because you almost design in an elastic stage. So is there any other proposal, like to increase that performance level without reducing the R, for example? How can you increase the ductility of such system, for example? Thank you.
Okay, thank you for the question that given to me. I would like to answer the first question. In the capacity spectrum, I shown before in my presentation, the capacity spectrum is shown the brittle failure. And as I mentioned in the introduction also, the failure of spoon pile is brittle failure. So for this purpose of increase the ductility, I investigate one of method that proposed before in some studies, that the spoon pile is infilled with a concrete and normal reinforcement. And after I ran a pushover analysis, it shows that the failure is stay in the brittle failure pattern. because the ductility is not shown higher than been expected before. And as I shown in the presentation, I use R value first is 3.5 in the linear elastic method because I expect the ductility is become higher after I infill the concrete and normal reinforcement. But after the burst analysis is done, I found that the capacity is not sufficient enough for resist the demand earthquake, and so I conclude that the R value should be reduced, and in this case I reduce the value to 1.5. Okay.
So when you consider the infill, you don't increase the ductility, you said. Could you explain or elaborate, like why is it the case? Why don't you increase the ductility by having the infill? Like, is there any reason?
Because I think the focus of my study is to investigate the method of concrete infilling method. So I stayed on this method, and what I could do to achieve a performance point in the ATC40 method is to reduce the response modification factor value. Yeah, I hope I answer your question.
Okay, thank you. Thank you very much.
Okay. Is there any additional question from the audience? How about from online participants? If not, then okay. Yes, please.
Sorry, Professor. Maybe I give additional information to Mr. Rafin. Actually, he tried to improve the ductility of the slab-on-pile structure with the concrete infill from the top and the bottom. However, when we try to calculate with numerical model with the moment curvature analysis, the result not many improvement of the ductility. So this result also is new information that give infill concrete not so significant for the moment curvature ductility. Maybe shear strength maybe increase like this. And then so one solution is suggestion is the better is using the near to elastic design with our seismic modification factor is 1.5. So it's also the suggestion for the designer in Indonesia should be aware when the design the slab-on-pile. It is not ductile like the RC column, but it's different like this. So maybe another next step maybe when we can develop another seismic device for the slab-on-pile or modification the structural configuration of the slab-on-pile by adding some damper like this. Maybe like this. Thank you.
Okay, is there any additional question from the audience? How about from the online participants? Maybe I can, is there any? Okay, then I can give back the stage to the Master of Ceremony.
Ladies and gentlemen, we will start again at 5:10 p.m. So please wait here. Thank you.
Hello, good morning, everybody. I would like to describe our special buildings, which is called STLC buildings. STLC buildings stand from Smart and Green Learning Center.
The STLC buildings is probably the first building in Indonesia that use a seismic device which is called a viscoelastic damper.
As we know that in Yogyakarta, the earthquake is very high, and we have a potential high earthquake occurring in our city. In the building, we have a reinforced concrete frame structure, and we put as many as 102 seismic devices.
This rubber damper have a 40 by 40 centimeter square and 2 centimeter thick. The capacity of the damper is about 40 ton or 400 kilonewton.
This device is very complex because the behavior is not only depend on the displacement, but also depends on the frequency during the earthquake.
It is divided into groups. From the first to the 7th floor, we put 2 sets of seismic device, 3 of them in X direction and another 3 is in Y direction. And another 30 seismic dampers we placed on the 7th floor to 11th floor.
The challenge regarding to the construction of SCLC is related to the preciseness, and the second one is related to the schedule matching. Because the damper holder is prepared in Indonesia, while the damper itself produced in Japan.
This damper are designed to reduce lateral displacement, so that the interstory drift should be less than 1%. These dampers, if we don't use this damper, so the lateral interstory drift will be up to 2%.
When the earthquake entering our structure, the energy has been reduced, maybe up to 60 or 70%. And that's why the effect of earthquake on our building will be much better.
So we hope that using these dampers, people using this building will be more comfortable.
In this case, the earthquake energy will entering our building in full capacity. However, at every floor that we have, it will be reduced by the damper.
This building also equipped with 13 accelerometers. There are 3 axis accelerometers on base or on the ground floor, and there are 2 axes in certain floors, so that we can monitor the lateral displacement at any time. So at certain displacement, these accelerometers can alarm, and hopefully that everybody using this building will be evacuated. Yeah. So more safer for people using these buildings.
We are going to use this seismic device in modeling a structure. Of course, we should make sure that all the parameters that will be used in the model should comply with the real behavior of the device. The device should be tested before we use it in the model and before we use in the real building.
So we have to consider the situation. Related to the preciseness, we have only 2 millimeter tolerance in order to make the damper work properly. And the second one, related to the construction schedule matching, we have to start the construction while the damper is under production, and then pack and ship to Indonesia. So in terms to schedule matching, I have to modify the method, which is we use the dummy damper, which is I use steel plugs in the position of dampers And then once the damper come to the side, we will release the dummy damper and then replace with the original ones.
There are two objectives of testing this device in the laboratory. The first one is we are going to find out the proper parameters to be used in the modeling. And the second one, we need to make sure that the behavior of this device satisfy the code.
So this kind of method is actually really interesting because we have to check the preciseness of production in Indonesia to match the standard production from the damper production in Japan. The second one, we have to match about the scheduling, how to maintain the progress and the sequence to the arrival of the damper from Japan.
In SNE 1926 in 2019, this device is categorized in chapter 13 about dampers. And it is said in the code that before we use this device, we should carry out laboratory tests to check the behavior of this device, whether it is satisfied or not.
So I think in terms of the use of the damper, this is the two aspects that we have to really concern. Number one is related to the construction method, preciseness, and then the second one is how to match with the schedule matching for the construction. This is the situation where the construction become more challenging, and we are very thankful to all parties, from the consultant, the producer, and the contractor, to make the construction of damper structures become to the reality. And I would like to promote the use of this kind of damper because this is the very first time application of its kind in Indonesia, and this kind of damper is having big opportunities, not only for new building, but also it's very, I think, good opportunities to implement in the existing building.
Hopefully, when the earthquake is coming and struck our structure will behave better and better, not only at one earthquake, but it should be at every earthquake that we have in the future.
In order to retrofit all the seismically improve the performance of existing buildings. So we do hope that the use of damper system of its kind, which is made of viscoelastic high rubber damper, is become more engineering communities, and then at the time probably we can use it in more kind of construction, both for new building or for existing building for seismical improvements. Thank you.
Welcome back, ladies and gentlemen, to our last agenda of 5th International Conference on Earthquake Engineering and Disaster Mitigation Seminar. For closing our amazing event, we will have a closing remark by the head of Civil and Environmental Engineering Department. Please welcome Prof. Teguh Faisal Fatoni.
Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, the Honorable Guest, Dean of Faculty of Engineering, the Secretary General of International Association of Earthquake Engineering, Professor Koichi Kusumoki, all keynote speakers, invited speakers, Organizing Committee of the 5th International Conference on Earthquake Engineering and Disaster Management, representative from Indonesian Earthquake Engineering Association, presenters, and all participants. It is an honor to deliver this closing remark on the success of the 5th International Conference on Earthquake Engineering and Disaster Mitigation. We successfully hosted this hybrid event for 3 days, consisted of 4 plenary sessions with 8 keynote speakers from Indonesia, Japan, Canada, and the United States. We have 20 parallel sessions that effectively delivers 76 papers. A short course led by 6 panelists, which will be held tomorrow. During the last 2 days, there have been 88 attendants in the auditorium and almost 300 online participants. We believe we all participated in a thoughtful and interactive discussion. I would like to thank 2 distinguished keynote speakers who shared their inspiring work, all the presenters, participants, committee, reviewers, and all parties for their enthusiastic and dedicated work to make this event happen. I'm extremely pleased that this conference was well attended by a wide range of stakeholders, ranging from academia, governmental officials, and policymakers, to industry practitioners and experts. Providing forums for establishing a dialogue and expert network such as this one, which we believe will be beneficial to you. Even so, we would like to see the sustained development and deployment of diverse disaster mitigation systems. Importantly, policymakers at the highest ranks of decision-making are no better equipped to formulate a strategy and techniques directed at enhancing the disaster mitigation system to minimize the risk, save lives, and preserve the environment. Lastly, I'm looking forward to continue our collaboration on the next International Conference on Earthquake Engineering and Disaster Mitigation. We wish you the best of luck in your future endeavors. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, Professor Teguh Faisal Fatoni, for the great closing remark. Ladies and gentlemen, we finally get to the last session of our event.
But before we wrap up the event, I'm happy to announce the 3 best presenters. The 3 best presenters are Roy Miliardi, Calvin Sandi, and Tri Suryadi. Congratulations to all the best presenters. To all presenters list above, please come forward to the stage.